is my pleasure to present to you Jean-Pierre Bourguignon, who is going to give a Pedro Nunes lecture. So the Pedro Nunes Lectures is an initiative of the CIM, Centro Matemática, supported by Portuguese Mathematical Society and Fundação Gulbenkian. And it aims at bringing outstanding mathematicians in order to boost the interest in mathematics, but in science in its global sense. The Pedro Nunes Lectures have been dormant for a couple of years, but New Direction of CIM decided to revive it, and I would say that we could have started in a better way. So Jean-Pierre Bourguignon is a geometer with a strong background on mechanics, and he happens also to be the president of the European Research Council and former director of IHÉS. He gave us a wonderful interview that is going to appear in our CIM bulletin, which I invite you to look for it at our website. And as you can see, he's going to talk to us about general relativity and geometry, interactions and missed opportunities. So thank you very much for accepting our invitation, and it's a pleasure to welcome you here.
Thank you very much. It's always a pleasure for me to be in Portugal. Last time I was in Porto, I was part of a team to evaluate the department, so maybe it's nicer now to be here in a different capacity. So the topic of my lecture this afternoon is really, of course, one can talk about general relativity as such, but my point is a slightly different one, which is why is this theory interesting for geometers, what it did to geometry, and also in the other way, what the geometry or geometric ideas can bring into general relativity. So this is actually the starting point is, of course, that this is just one example one can take of interactions between geometry and physics in general. There have been many, many instances in the 19th and 20th century where really geometry and physics have interacted. And therefore, I just took general relativity as one theory which definitely has had a number of very distinctive influence on development of geometry, but also some missed opportunities, as I will try and show you. Just to stress, and this is really my point, is that quite often the points of view of mathematicians and physicists is quite different. And depending which point of view you take, you come up with this conclusion or that conclusion, and actually sometimes it's very important to use the conclusion of the other one. And this has not always happened. And therefore, I will try to give a number of examples taken from the development of the theory of relativity, and which has an impact on geometry. And by doing that, actually, I'm going to not to discuss, where I could have discussed actually, some extraordinary, interesting and difficult results which have been obtained on the, as you know, the field equation of general relativity, so-called Einstein equations, which is a very interesting system of nonlinear equations. And in the last 20 years, formidable progress has been made on the solution of this system. And it has really pushed the theory of nonlinear PDEs to new heights. And particularly the two people who really contributed a lot, but after that there have been very, very many people who have been working. Demetrios Christodoulou, who was really coming more from the physics side, and Sergiu Kleinerman, who was coming more from the mathematics side. So this is more or less what I want to discuss. And here are the various parts I'm going to be presenting. So of course, from where is the theory of general relativity coming? I want to spend a few minutes on somebody who sometimes is not presented as a central figure, when I personally think he is a very central figure, who's Gregorio Ricci Cobastro. And of course, the Ricci curvature, which is very critical in the Einstein equation, it comes from his name. But of course, the very important step has been the introduction of general relativity, and which both from the physics point of view, but mathematics point of view, is really a giant step. Then immediately after the occurrence of general relativity, several people have tried to generalize it in various ways. The first one was Hermann Weyl, And I will explain how this had a very significant impact on conformal geometry. Then another generalization which came very, very soon after the presentation or introduction of general relativity by Albert Einstein was the so-called Kaluza-Klein theory. Actually, one should say the first generalization was really Kaluza alone. Klein came 10 years later. And one missed opportunity I want to discuss, although there is also some mathematics to be done there, is connected to some paper by Cornelius Langsors, much later in time, just before the Second World War. And then I want to discuss what can be taken from the so-called Arnovit-Desem-Misner approach to Einstein equations, and in particular how this connects to the so-called Ricci flow, which has been very, very important recently in geometry and topology, as you know, because it led to the solution of the Poincaré conjecture. And I want to finish with another generalization of general relativity, which is called supergravity, and how it connects to interesting problems in geometry. And then I will try and conclude. So what about the praise tree? Well, you can go back very far, but maybe one starting point which is interesting is this famous habilitation by Riemann, was defended on June 10, 1854. And as you know, this was the part of his work, which was not his research work, but the very typical situation in Germany and actually in France for many years. This is not anymore the case, which is called a proposal by the faculty, which meant that the faculty proposed 3 topics to Riemann, and a few weeks before the defense, the faculty choose out of the 3 which one should be presented. And actually to Riemann's surprise, the faculty chose this topic. Actually, it's Gauss, who was member of the jury, chose this topic, which is assumptions on which geometry is based. And therefore, it means that the work of Riemann on this has been really produced in a very short period of time, and really on command. I mean, it was really commissioned to do something about it. And it's a very interesting text, which was published only after Riemann's death, actually. Although it's a piece of geometry, there is not a single picture, and there is only one formula. And of course, Riemann doesn't tell you how he got the formula. Of course, there are papers. I mean, in particular, he submitted a paper to the French Academy, a very interesting competition on how can one describe the diffusion of heat in an inhomogeneous body. And in his submission, actually, he does unravel some of these calculations. Anyway, it's very interesting if you read the text that, although, of course, it's a piece of mathematics, he's really concerned about physics. And actually, at that time, he was really thinking about ether, which was this kind of background that nobody knew how to formulate, which was supposed to support all kinds of physical phenomena. And so this is a part which is called application on space, and space is really meant as the physical space. And of course, he does discuss both the very large and connects to astronomy, but also as a paragraph on the very small. So for him, these physical considerations embraced both the, I would say, what one calls today really astrophysics, and at the same time, really the very small particles. And so he even discusses how one can really use the notions that he has introduced to discuss not only continuous objects, but also discrete objects, which it's not clear how one can do it in his setting. And he really even discusses how one can check whether the space around us has really this more generalized structure that he describes, or if it's really usual Euclidean space, flat space as one calls it now. And he's talking about actual measurements that could reveal whether you are in one space or another one. Anyway, so this was really this paper, this document, fundamental document of Riemann, which is the birth of Riemannian geometry. And as you know, the whole purpose is to discuss what is the geometry behind an object which is in local coordinates. So you take a local coordinate system, xi can be written as gij, dxi, dxj, which is the local expression with the symmetric matrix, symmetric, but of course positive non-degenerate. This is the scalar product And of course, the new feature that he's considering is that these Gij are really depending on the coordinates. So in Euclidean space, you can always find a system of coordinates in which the Gij are constants. But here you're considering general situation. So this is the geometry that he discusses. Another document I want to talk about, because it's not so well known, and it's actually somebody who is connected to Portugal in some way. He's a British person, but spent a lot of time in Madeira, who is William Kingdon Clifford. So so Clifford has done many different things. In a sense, his life is very parallel to that of Riemann. That is somebody who has been able to touch many parts of mathematics. Also, his health was very fragile as Riemann. Riemann died of tuberculosis, but was very weak for a number of years. In the case of Clifford, it's the same. And also he died of tuberculosis. Actually, he died in Madeira. And so it's interesting that he has a paper, a short paper, which is called On the Space Theory of Matter, which he published in 1876. And here I'm quoting Clifford. I wish here to indicate a manner in which these speculations may be applied to the investigation of physical phenomena. I hold, number one, that small portions of space are in fact analogous to little hills on the surface, which is on the average flat, namely that the ordinary laws of geometry are not valid in them. Second, that this property of being curved or distorted is continually being passed on from one portion of space to another after the manner of a wave. Third, that this variation of the curvature of space is what really happens in that phenomenon which we call the motion of matter, whether ponderable or ethereal. Fourth, that in this physical world nothing else takes place but this variation subject to the law of continuity, which is a fantastic anticipation of what general relativity is. And you see the date, 1876. Of course, there is no formula, it's just still abstract considerations, general considerations, but nevertheless, it's very remarkable that, in particular, what is the underlying element here is that it's the phenomenon of gravitation should be directly connected to the geometry of space-time. And so this text is really, I call it a visionary note, but it's quite a remarkable document. So this is still prehistory. This doesn't give rise to no theory in detail, but maybe it's connected to the fact that Clifford's life was too short. And anyway, of course, the next stage which I want to come to is the stage at which Einstein, you know this year, extraordinary year of Einstein, 1905, in which he made three fantastic discoveries in terms of physics. So the one I will focus upon is the one which has to do with the special relativity. And actually, the work of Einstein on this came really after some work by Lorentz, the Dutch physicist, who really had been taking very seriously the experiments by Michelson and Morley, which, as you know, were trying to detect a motion of, when you wanted to check the light, whether the motion with respect to the ether. And then by the Michelson-Morley experiments, you realize that it doesn't seem to be, if there is a motion, you cannot detect it this way, which of course gives ground to the idea that maybe the speed of light is an absolute. And of course, from this on, Einstein did a number of so-called Gedanken experiments, or experience of the mind, to really think of how should one develop physics in order to take this into account. And actually, the two mathematicians who really transformed the idea and the comments and the very important philosophical and physical discussion by Einstein into a piece of mathematics were Henri Poincaré and Hermann Minkowski in parallel, more or less. And what is very interesting is the difference of style between the two. So the approach by Poincaré is presented in an article published in, actually in the compte rendu from Sicily. And the title of the article is called Le Mouvement de l'électron, so which means that he's really looking at it from the point of view of a physicist, although the comments he makes is that if you look at the very basic transformation that Einstein has been using, which came from Lorentz, so-called boost transformation. If you're interested in this four-dimensional space, that is 3 dimensions of space and 1 dimension for time, if you look at this boost transformation and look at the group they generate, then you realize that the group they generate is a group of isometries of a generalized metric, so it's not anymore positive definite, but a matrix with as signature 3, 1, or 1, 1, 3, depending which sign you want to give to the time. And so it's very interesting to see that from very concrete transformations, that is really very small objects, if you think mathematically into in terms which are very familiar for people at that time, namely using invariant theory, you realize you construct a geometric object, which is this well, generalized metric with signature 3, 1 or 1, 3 as you want, which this indefinite metric is of course the key object which is behind the theory of special relativity. In the case of Minkowski, actually he presented his approach is very much in the spirit of the elements of Euclid, and that is it's really very axiomatic, and so it starts from a 4-dimensional space, which he calls, of course, space-time, because the 3 dimensions for space, 1 dimension from time, and the title of the article is called Raum und Zeit, space and time, and then he really builds from a priori using a generalized metric, an indefinite metric, all the elements which really allow to discuss in depth the special relativity. So this was of course, and then there were further developments around this, but typically that was the situation for a mathematical understanding of special relativity. Let me move back a little bit in terms of chronology, but I thought it was good to have this kind of a first movement until really general relativity approach, which is has to do with a development from the geometry of Riemann by various people. And quite often the name which is put forward as the next contributor is the name of Christoffel, which I think definitely can be mentioned, because there is a very interesting paper by Christoffel in which he discusses the very natural question, very much related again to invariant theory, which is the question that imagine you have 2 systems of coordinates xi and y alpha, and suppose you give yourself a metric G, which is gij dxi dxj, and you give yourself another metric, which is h alpha beta dy alpha dy beta, and you ask yourself, may I find a diffeomorphism, that is a transformation from one system of coordinate to the other, in such a way that when I pull back using this transformation h, I get G. So what are the conditions for 2 metrics to be actually the same geometric object, that is up to diffeomorphism the same object? And this is in discussing this question, which is a very basic question in geometry, of course, in this Riemannian geometry, that he introduces the famous Christoffel symbols, which he denotes by this bracket notation, which we tend to call now with a gamma. But that notation by Christoffel was this one. And it's interesting because, of course, these quantities are extremely important in Riemannian geometry, except in the case of Christoffel, if you read the paper, it's just a shorthand notation for something he has to carry over and over again. But there is no hint what it does, why it's useful, and so on. So here comes Ricci, for the reason that he is the one who really understood what these symbols were for, and he's really the one who really introduced what one now calls the covariant derivative notion, and he really was able to establish the computation by Riemann in a very systematic way. And he did that in a number of publications, starting in 1888. And the first one, published in Italian, in the part of the publication of the University of Padua. And this is really where, in a sense, for the first time, the concept of covariant derivative is formally developed. He did that also a bit later in a publication in French, in the Bulletin des Sciences Mathématiques. And of course, the paper which is usually used as reference for a very systematic presentation of these notions is this famous paper called Méthode de calcul différentiel absolu et leurs applications, published in 1900 in Matemática and Allen. So I find it, I was editor of Matemática in Ireland at some point, so I find it interesting that two Italians publish in French in a German journal. So maybe it shows that Europe existed at that time more than now. Anyway, so I'm not meaning that I'm not mention anything in English that I'm for Brexit, but no joke on that. Anyway, so what's very interesting if you read this article, which is if you don't know it has been written 1900, you could believe it has been written yesterday. Fantastically, clearly written, all concepts are in place, very systematic presentation, including a lot of applications to a number of parts of physics, mechanics, and so on. So this is a really remarkable maturation of things from the first paper by Richie Corbastro, which is really just a moment where something is understood to really when the method becomes, and it's interesting that the title of the article is Method of Methods of Absolute Calculus, Differential Calculus. Anyway, of course, so this is the paper in Mélange that is in the Bulletin des Sciences Mathématiques by Richie. So this is the reason why usually Richie is called just Richie, because his full name is Richie Corbastro, but even when he signed just Gregorio Ricci, and he was professor in Padua. And so this is where he really discusses what I wrote well, that's exactly what I wrote on the left, and then discusses everything which goes with it. Anyway, of course, now that I'm coming to why Ricci is remembered is for something which is called the Ricci curvature. So, and particularly in connection with general relativity. So one thing which was very important, of course, I told you in the essay by Riemann, there was just one formula. And this one formula is very simple. It's a formula which says, imagine that you have your metric Gij, and in a sense you, in a generic point, so, and you can compute, so imagine your system of coordinates centered around a point P, which of course will have coordinate 0, 0, 0. And then the whole point is to say that you have an expression of the Gij in terms of their value at the center, so let me call it P. And then there is a correction term, and actually if you take your system of coordinates in the right way, which we now call normal coordinates, actually the first term which appears here is something which is this Ijkl, so x, I'm sorry, Ij, no, I'm sorry, I should not write it this way. Well, let me write it Kjl, xkxl, plus, so it's some kind of a local expansion. And remember I told you that this notion of metric is more general than Euclidean geometry. And of course, what measures the deviation from being Euclidean is exactly the existence of this quantity, which is the Riemann curvature tensor, which measures, in a sense, the correction term you have to introduce. And if you choose your coordinates normal, you don't have any first order term. The first term is quadratic. And of course, actually, the vanishing of this would also kill off the next terms, because they obtain from derivatives of this tensor field. Anyway, so this was the only formula which was there. And as I said here, this object, the Riemann curvature tensor, measures the deviation from a Riemannian metric from being Euclidean. And of course, in another paper, 1904, Richie Corbastro introduces a quantity which is the one I defined here. So typically, it's, as I said, it's a fourth order tensor, spontaneously a tensor which is 3 times covariant, 1 time contravariant, which means that R can absorb 3 vectors and gives me a vector. And so if you do what I just did, namely if you're interested in the map, which to 2 vectors xy is, you associate the trace of the transformation from z to rzxy, then you get something which is a bilinear form. Actually, you can prove that it is automatically a symmetric bilinear form. And so this is an object which is extracted from the Riemann curvature tensor. And actually, when he did that, introduced this quantity, which is extracted from the Riemann curvature tensor, his motivation was very geometric. Actually, a theory which was developed before Riemann was the theory of hypersurfaces, in which people developed the notion of principal curvatures. And in particular, it was known if you have a hypersurface in Euclidean space, then you have some preferred directions, which are of course, the directions of these principal curvatures. And so he thought that maybe you can do the same in any Riemannian space. And actually you can, because you have the scalar product, you have this symmetric to tensor, you can diagonalize the symmetric to tensor in an orthogonal basis. And when you do this, you have this principal, the analogous of the principal curvatures. So that was the motivation to introduce Ricci. Ricci was a motivation to introduce at each point of a Riemannian space some preferred direction. What is kind of funny is that I don't know any theorem in geometry which uses this. And of course, so the motivation was very natural, but it didn't prove to be of any use as a geometric tool. But of course, what is of central use is this object, Ricci. So in a sense, it's interesting to see that even a great mathematician as Ricci, who had understood a lot about Riemannian geometry, when he introduces the Ricci curvature, actually missed the target. Of course, he introduces a very critical element, but not for the reasons he thought was interesting. Anyway, so let me move on to general relativity. So 1913 is really the turning year, where after struggling for some time, Einstein and his neighbor in ETH, Marcel Grossmann, they were students together before at ETH, they really made their first attempt to describe a generalized theory of relativity, theory of general relativity. And the way they did it was by making a huge shift. From the epistemological point of view, it's really a fantastic jump, because the traditional theory of gravitation introduced by Newton was really the key element was the so-called gravitational potential, which is a function. So in a sense, to describe gravity, what you needed is to look at the field generated by a mass, which was a scalar function. And then all of a sudden they say, well, maybe that's not the right notion to use. And they said that maybe the right field to consider is not a function, it's a two-tensor field of, which is the general of like the Riemannian one, but of type indefinite metric, signature 3-1. So you go from a function as your basic object to a tensor field over its four-dimensional space is a huge jump. And of course, and it means that you leave the domain of special relativity, where the metric was there, but with constant coefficient, like the Euclidean metric in Euclidean geometry. You had the Minkowski metric in the indefinite case with signature 3-1. And then you go, therefore, to do the same jump from Euclidean geometry to Riemannian geometry. You do the jump from Minkowski geometry or to what one now calls Lorentzian geometry. And of course, what was bad news for 1913, of course, for theory in physics, when you have identified what is the right field, you have to find the fields equations. And unfortunately, in this paper, actually two papers back to back by Einstein and Grossmann, one on physics, one on the mathematics, what they propose as a field equation is just wrong. And actually badly wrong, really badly wrong, because the whole theory is supposed to be completely covariant, and even the equation they propose is not covariant. So it's kind of disappointing. But of course, when you have people with the strength of Einstein and Grossmann and people around, finally it's just a temporary problem. And they solved it, and it was solved jointly by Einstein and Hilbert, not lightweight, of course. And the way they did it finally, I mean, they were struggling for a number of time. If you look the description of all these exchanges in the book of Pais, for example, you can see that it was very, actually, cooperation, but also competition between the two, very much so. And you can realize, actually, that they were, when they had done the calculation, they waited 1 or 2 weeks before they sent it to the other one, and so there was interesting competition. Anyway, so the key new idea is the one which I present here. From the Ricci curvature, which is a symmetric tensor, since you have the metric, you can take a trace of this, so you transform the Ricci curvature, which was a bilinear two-form, into a function, and so that's the so-called scalar curvature, which is this function. So now imagine you consider the Lagrangian on the space of fields. You know, remember, my fields are Minkowski or Lorentzian metrics. So to this Lorentzian metric, I associate a number, which is the integral of a space-time of this. Of course, you need this to make sense. That is, if this is infinity, you're in trouble. So you hope that your space-time is flat enough at infinity that this integral makes sense. And then you do the calculus of variation on this. That is, you look at the Euler-Lagrange equation for this functional, and you end up having the so-called Einstein equation. And what is remarkable for this Einstein equation, it contains Rg, which basically comes from the variation of the scalar curvature, and then you have a correction term, which is minus a half Sg times g, which comes from the variation of the volume element. And so this is the left-hand side, which is given by the, if you have an empty space, that is, if the only physics you are dealing with in the space-time is gravitation, you should put 0 here. Of course, when there is some other physics, the other physics is going to contribute through the so-called stress energy tensor, which you have to manufacture for each type of physical interaction, electromagnetism and all kinds of other things. Okay, so this is this wonderful system of equation. The unknown is G, and this is, you will see soon the formula which relates G to R. You will see it's a second order nonlinear system of partial differential equations, which is kind of heavy, as you will see. It's a non-trivial system. And solving the Einstein equations means finding G, knowing, for example, you give yourself T, could be 0 if the space has no other physics than gravitation. It can be something else if you know you have to describe the physics properly. And so this is the problem of general relativity. And of course, since this system is very difficult, it took a long, long time to get really satisfactory solutions for this system. Nevertheless, very early on, people could find some special solutions. And for example, one which is very important, so-called Schwarzschild solution, which is related to the field generated by a symmetric star, typically like the sun, the outside field. And so there were some known examples, and people developed many interesting examples. But to find a general solution to this system is a very, very hard problem. And as I said, in recent years, fantastic progress has been achieved. So let me move on to the immediate generalization which was suggested. One came, so the theory of general relativity, as I told you, was started really in earnest in 1915. And so 1917 already, Hermann Weyl already made an attempt to, he wanted to unify general relativity, that is the theory of gravitation in the view of Einstein, and electromagnetism. And the way he did that was actually very interesting because it's really was the first example of a so-called gauge theory. That is a theory which has some kind of a natural local invariance and that you want to elaborate upon, which actually you need, and that's something clearly Hermann Weyl understood immediately, which is very much connected to understanding a general concept of covariant derivative, not only the one that you're using in Riemannian geometry, but a more general concept. And actually, if you look at the way he developed that, what he was really doing is being interested in the so-called conformal classes of metric. That is, a metric G is the metric typically, again, I'm in the context of general relativity, so it's an indefinite metric, signature 3,1. And you look at all metrics which are obtained from this G by multiplying by a function. Since I still want my function to be always positive, I just write it as an exponential, just because I insist on the function being positive. And therefore, and then he developed, so for him, the electromagnetism should be really hidden in this U. And G, of course, describes the gravitation. And of course, by doing that, of course, he had to study this new geometric object, which is metrics up to a conformal factor, and which is really the basis of what one calls conformal geometry. Conformal geometry is the geometry of conformal classes of metrics. And he found a number of interesting facts about conformal geometry. In particular, that if you look at the way, so if you have a metric G, you know you have the Riemann curvature tensor attached to it. If you look at the metric G twiddle with this factor here, you have another Riemann curvature tensor, because that's another metric. If you compare these two Riemann curvature tensors, actually they have a lot in common. Particularly what they have in common is a component which is called now the Weyl curvature tensor, which is a very significant piece, actually the most complicated piece of the curvature. So changing a metric just by multiplying by a function changes the curvature, but in a way which is very interesting. And what is quite remarkable is that if you look at the full Riemann curvature tensor, knowing Ricci and knowing Weyl determines completely the Riemann curvature tensor. So in a sense, the part that Hermann Weyl had introduced, namely looking at the conformal classes of metric, pushes you in one part of the curvature tensor, and the Einstein equation with the Ricci pushes you in the other direction. So this is kind of interesting. But in the end, this approach by Hermann Weyl didn't prove fruitful for the unification of gravitation and electromagnetism. Another attempt which came at approximately the same time, slightly later, one year later, is due to Theodor Kaluza. Actually, in 1918, Kaluza wrote a postcard to Einstein to submit a paper which Einstein did not immediately accept for publication, which was another approach to unifying gravitation and electromagnetism. So what is it? It's interesting. It's again a mathematical construction, which in itself is a very interesting one. So you start again with a metric on space-time, so Lorentzian metric, and you imagine you have electromagnetic potential on this space-time, which I call psi. And then the idea is to say, well, my real, maybe a real is a word of a mathematician, but for physics it's not a real thing. But the right space to think about is not M, but the product of M with a line. And of course this M twiddle. And on this M twiddle, I'm going to put a new metric, so it's a 5-dimensional space now, G twiddle, which I do using the following trick. So what is the trick? The trick is the following one. Of course, if I take this M twiddle to M, I have a natural projection, which consists in forgetting about the R component. And then if I do the following thing, so psi exists on M. Using psi, I can lift it up to the 5-dimensional space. U is a function of R, so is my parameter along R. So I can create upstairs a new differential one forms, which is du plus pi star of psi. If I tensor it with this gives me a symmetric bilinear form. And of course my G, which is a Lorentzian metric, I can lift it up here. And of course pi star G is living now on M twiddle. And so now I have, if I forget about phi, I have a quantity which is still a Lorentzian metric in 5 dimensions. Because I had the signature 1, 3 here, and I had something positive definite, that's a square of the same form. So it's a 1-4, now it's a 1-form bilinear form, so indefinite metric. I still need something here which more or less tells me something about the units on my R. What is the 1 sitting there? And so this is the trick, that is how from G and psi you create a new metric on the 5-dimensional space. And of course now what was the discovery by Kaluza, if you compute the Ricci curvature of this new metric in terms of all the data, G, psi and phi, there is a wonderful formula for this, which is the following thing. If you write that the Ricci is 0, actually there is a comment I should have made, I'm sorry, I should have done it. I'm moving back. On the Einstein equation, if you have 0 here, just by taking the trace of this, you see automatically that for the Einstein equation for the flat space is actually Ricci equals 0, because just by taking the trace, if 0 is here, if you take the trace, you're going to see that S is 0. So if you are solving this equation with 0 on the right-hand side, actually it means you are solving the equation Rg equals 0. So what Kaluza was claiming is that if you write the equations Rg twiddle equals 0 in the 5-dimensional space, you end up having not only you find the Maxwell equation, you find the coupling of the gravitation to the electromagnetism, which you know you manufacture exactly the right T, the stress energy tensor. And so it looks like you have solved the problem, which means you can incorporate electromagnetism into the Ricci flat space in 5 dimensions. The only thing which is not completely satisfactory is that I have to not discuss too much the phi, because in order to do that in the proper way, you need actually phi to be 1, a constant, which actually is physically not exactly acceptable. So this is the gap, but still it shows from the mathematical point of view the relation between this 5-dimensional calculation and the 4-dimensional calculation is really striking. And actually what is behind is something that mathematicians didn't take seriously for 50 years, where they should have, which is you should have been looking for situations like this one, where you have a projection from a larger dimensional space to a lower dimensional space, and look at formulas which relate what happens upstairs and what happens downstairs. And it was only done very late by Barrett O'Neill in the so-called theory of Riemannian submersions. Riemannian submersions relate to the fact that you insist on having a metric on the base and a metric on the total space, which are related in an interesting way. That is, they are really mapped using the pi. So anyway, so it shows that this was an opportunity for pushing mathematicians not only to study under objects, like submanifolds, but to look at bundle theory, which is the theory of projections from larger space to smaller space. But it took almost, 40 years to have this done. Anyway, so that was Kaluza. I'm moving now to, of course, you can say many more on Kaluza, because one usually calls this Kaluza-Klein, but Klein came 10 years later, because you see, well, the main transformation that Klein introduced, Oskar Klein, not Felix Klein, don't be confused. Oskar Klein showed that if you are serious about quantum mechanics, which appeared a bit later, you need to quantize this theory of electromagnetism. And then having R is not the right thing, because R, you cannot quantize it. But if you replace R by a circle, all of a sudden, then you have a quantization linked to the fact that you have to count the number of times you go around the circle. And then, so you can rethink the theory of Kaluza-Klein, and now using Klein, indeed, as a theory for a bundle in which you have an action of S1 on this, and it was generalized in the so-called non-abelian Kaluza-Klein theories, where you use as a group which will act on the total space, which is a group of invariants of some physical interaction. So either the weak interactions or the strong interactions, so SU2 or SU3, and so on. Anyway, I'm moving to Cornelius-Langsource. So this is something really quite extraordinary, which is the following thing. So actually, it was known already since the mid of the 19th century that when you are in 2 dimensions, the functional which I used, forget about that for 1 minute, used for my potential, you remember what I use as potential as Lagrangian for the general relativity was the so-called total scalar curvature, which is the quantity with, the integral which associates to metric just this number. But actually, if you do this not on a 4-dimensional space, but on the 2-dimensional spaces, there is the famous formula by Gauss and Bonnet, which says that this integral on a closed surface is actually something which is independent of G. So you see, it's actually 2 pi times the Euler characteristics, the purely topological quantity. And so it's a very remarkable formula, because a priori when you write this, you expect this to be a function of the metric, but actually it's independent of the metric. And actually the fact that this happens in 2 dimensions, so I should have put a 2 here to insist that this is a surface. But what remains from this is in all dimensions, you remember when I described the Einstein equation, I told you that actually this S is connected to Ricci, connected to the full curvature tensor, so it contains the 2nd order derivative of the metric. And if you are used to the calculus of variation, if from your field you involve 2nd order derivatives, then the field equation will be twice the order. It should be 4th order. But you remember the Einstein equation is just Ricci minus 1/2 SGG equals T. That is 2nd order. So where the 2 orders have disappeared, they are directly connected to the fact that in 2 dimensions, this is a topological invariance, and what remains in higher dimension is that the higher order terms disappear. Anyway, so why do I want to speak about Langsource? Well, in the late 30s, people were, in general relativity, were interested in particular in some phenomena that astrophysicists were pointing to, which had to do with inflation. And he tried to look at more generalized Lagrangians than just the total scalar curvature. So of course, the next stage, instead of taking a linear function of the curvature tensor, you take a quadratic function. And actually, it's easy to prove that all possible quadratic functions of the curvature tensor, there are only three. It's a three-dimensional space. So you can look at all possible of these Lagrangians with indeterminate alpha, beta, gamma. So these are the three, I'm taking here, three possible quadratic forms on the space of curvature tensors. And then he noticed, if you choose alpha, beta, gamma in a certain way, in a very specific way, then actually the functional doesn't generate any field equation. So of course, for a physicist, it's a disaster. You are introducing a Lagrangian, and it doesn't give you any field equation. So he said, these are bad. Of course, from a mathematician, so of course, for him, bad luck. This is the bad combination. For a mathematician, it's fantastic, because you have found a new invariant attached to a metric, because the fact that this doesn't depend on the metric, you hope that this is going to be a topological quantity. And this is indeed the case. Actually, a priori, it's a differential invariant, but you can prove it's actually a topological invariant, because indeed, in 4 dimensions now, you have the fact that this integral, which is independent of the metric, is actually 8 pi squared, again, the Euler characteristic. So, again, the point of view, from the point of view of physics, you propose a Lagrangian, doesn't give you a field equation, it's a bad thing. From the point of view of mathematics, it's great, you have found a new topological invariant. So that's why we fight all the time. Anyway, so this was, I think, something quite remarkable. And even, sorry? Sure, I know. Of course, no, I didn't say that this was not interesting. I said that for other coefficients, of course, you can do a lot of interesting physics, actually, and a lot of physics has been done. So anyway, what is very interesting, this was published in the Annals of Mathematics in the same volume as a paper by, the first paper actually by Chern. And later on, so that was 38, 44, Chern published again in the Annals of Mathematics a new approach to the Gauss-Bonnet theorem, which is very interesting. So again, it's the Gauss-Bonnet theorem in 2 dimensions, but immediately he was able to generalize. And what is very interesting about this new proof is the fact that this new proof of the Gauss-Bonnet theorem is that the whole idea is actually using bundle theory. So the new idea of Chern is to say that if you want to prove in an efficient way the Gauss-Bonnet theorem, you have to lift the whole situation of your manifold to actually its sphere bundle. And when you lift it to the sphere bundle, which is exactly doing Kaluza-Klein theory, actually you can get a very easy proof of the Gauss-Bonnet theorem. Not only this, but you can generalize it to any dimension. And in particular, you get the formula by Langsos. And I was very surprised that when I told Chern about this formula of Langsos, that didn't know about the paper by Langsos. So it was interesting. And of course, this happens in every even dimension. So in 4 dimensions, it's a quadratic function of the curvature, which gives you Euler. In 6 dimensions, a cubic function, and so on and so forth. In odd dimension, it's always 0, so you don't get anything interesting. Anyway, let me move on now to my last 2 parts, which have to do with the so-called Arnovitt-Dazer-Misner, ADM, approach to the Einstein equation. So it's the first time you think of it, it looks like you are going backward, which is the following one. Actually, the first person who suggested this approach was Yvonne Bruard, and which is the following idea. The whole idea of general relativity is really to think about space-time. And so it looks like you don't want to go back to the idea of really separating space and time. You want them to be together. But actually, it happens to be very fruitful to think of the space-time as foliated by spaces. So, and then to have some kind of a parameter, which I use the letter T for, but it's not necessarily time. It's really just a parameter. And therefore, you can replace my G, which is really the four-dimensional Lorentzian metric. I can replace it, so that's the field which I'm interested in, into 3 fields, which is 3 curves of fields. So one is the induced metric on the, so GT is just the induced metric on typical, so this is, let me call this sigma t, so this is the evolution of space at time t or at parameter t. So you have the induced metric on this. Kt is just the second fundamental form of this hypersurface sitting in the, so this is space M. So this is sitting in, sigma t sitting in M. So, and then phi t is something which more or less measure what is the length of the vector d over dt. So this is using the metric g. So these are three parameters. So this tells you things about your clocks, in a sense. This tells you how the metric is induced and how this hypersurface is curved. So this is the situation. So in a sense, you replace a four-dimensional geometry by a three-dimensional Riemannian manifold, and then some kind of a special field on it, and then a special function. And then you can decompose the Einstein equation into two families of equations. The first one is typically an evolution equation. The first one is very trivial. It just says the definition of kt with respect to gt, second fundamental form. And the next one is the derivative of kt with respect to t in terms of all these quantities. And of course, the very important one here is Ricci. And I said two sets of equations. The other set of equations is so-called constraint equations. Why are they called constraints? Because if they are satisfied on one of the hypersurfaces, and then if you use the evolution equation, automatically it will be satisfied on all the next ones. So that's why it's called constraint equation. If you satisfy once and have the evolution like this, it's satisfied all the time. And therefore, it suggests to consider as a primary object the space of Riemannian metrics on a three-dimensional space, and because the evolution I was discussing is happening in this three-dimensional space. And physicists called it for a certain line superspace. And of course, you can, the total scalar curvature, which was the potential for general relativity, is of course a function of space of Lorentzian metrics on M. And the Einstein equation expressed the vanishing of the differential of this function on this space. M is four-dimensional. And actually, you can really discuss this in many different ways. But one way which is very, very important, one thing which is quite often presented as some kind of a constraint on this quantity, which is the left-hand side of the Einstein equation, can actually be completely understood in terms of this description. Let me move on to the ADM setting. So you remember, this equation, evolution equation, the first one, if you put the two together, so if you replace then kt by its definition in terms of gt, what you end up with is this quantity here. Assume I make the assumption that phi is a constant. So I forget about phi, I normalize it to be 1. Then the equation I get is this one, which says that writing the four-dimensional empty space equation is exactly to say that the second derivative of the family of three-dimensional metrics evolves according to minus Ricci plus a correction term. And so this suggests to consider differential equations involving the Ricci curvature in the space of Riemannian metric on the three-dimensional space. And actually the first person who did that was Thierry Aubin in 1970. I myself did some of that later, but the key formula is that if you look at how the scalar curvature varies, if you deform the metric in the direction of its Ricci curvature, you have a very nice formula. You get the norm of Ricci squared, and then you get something which is the Laplacian of the scalar curvature. So it shows in particular, if your metric you start with as a scalar curvature which is constant, the Laplacian is 0, and therefore deforming the metric in the direction of its Ricci curvature for a metric which has constant scalar curvature increases its scalar curvature, which is a quite surprising phenomenon. And therefore, it looks like one should really take seriously in the space of metrics, deforming the metric according to the Ricci curvature. Actually, this is something I proposed in 1979 in a conference in Berlin. So this was my question 324, which is to look at the flow on the space of metrics on which would be generated by this typically this vector field on the space of metrics, which is at metric G, you associate Ricci minus a correction term in the scalar curvature. Difficulty is that solving this differential equation is highly non-trivial. You're in infinite dimensions, so it's not true that any vector field has a flow. So, of course, finding the flow was a very difficult thing. So the first time you write the formula, you realize that Ricci, I promised you to give you the formula, which is kind of impressive the first time you meet it, which is really, there's a nice term here, which is something like a Laplacian of the same coefficient of the metric. This is more or less like a Laplacian. Then you have some correction terms which actually have to be there, and we actually force the equation to be degenerate from the point of view of PDEs. So the system is automatically a system which has some degeneracies. Actually, it's interesting to see that this resembles very much a derivative of the Christoffel symbols. Anyway, but there are tricks to get around this difficulty, the degeneracy. This was done by Hamilton and de Turck. And actually, it was very difficult to prove that. So what they did is to show that there is a local flow. But of course, now what is interesting is a global flow. And Hamilton proved some very, very nice theorem showing that if you add some geometric assumptions, then you can prove the existence of a global flow. Typically, for example, in 3 dimensions, if a manifold has positive Ricci curvature, then automatically you can prove the flow goes to infinity. I mean, you can get the flow without singularities. And then it shows that actually you end up being a round sphere. So it means that in a 3-dimensional manifold with a positive Ricci curvature is actually a sphere, if it's simply connected. But of course, much more happened later. Grisha-Perelman showed that even if there are singularities, you can still do something. Of course, it's much harder. So if you have a singularity, actually what he showed, it showed that the topology of the manifold is modified in a very controlled way, and that you can start with a new manifold, controlling enough the geometry that you can actually converge you can actually continue the flow. And in the end, because you can show that the number of accidents which can happen is finite, you can end up having a sphere. So this was the method that Perelman used to prove the Poincaré conjecture. Anyway, so in the meantime, there have been many more applications of the Ricci flow. So now I'm moving on to my very last part, which is supergravity and killing spinors. So there have been many generalizations of general relativity. One of them was an attempt to reconcile general relativity and quantum mechanics, and one of them is called supergravity. And it's interesting that this way, the classical way of doing quantum mechanics with general relativity led to the study of a number of very interesting geometric objects, typically in 7 and 11 dimensions. Which actually is connected to very rich geometries with a so-called exceptional holonomy, G2 in dimension 7, and also you could view them in dimension 8. And actually, one thing which was very important in this context of this so-called supersymmetry is to have the concept of an infinitesimal supersymmetry. And this occurred in the following way, that is so psi now will be a spinor field, so I'm not defining what a spinor field is, but I assume everybody knows. Physicists know for sure, mathematicians less, but that's life. So it's a field, psi, which satisfies this kind of equation, which is very overdetermined, which says that for any tangent vector, if I compute the derivative of my spinor field in direction x, it should be minus lambda x Clifford psi. So there is a natural action of vectors on spinors, the so-called Clifford multiplication, and it should satisfy this equation. And it's very interesting that the first time a killing spinor appeared in mathematics, or in physics if you want, it was in a paper by Penrose and Walker. They were studying the geodesics of a very specific family of interesting metrics in general relativity, so-called Kerr metric. And they realized that there was some kind of first integrals of the geodesic flow which you could describe in connection with this psi. So the first appearance of the killing spinors was not in relation to supersymmetry, but actually it was then studied. And actually, for physicists for quite some time, there was a discussion of describing all spaces which admit Killing spinors. And it was, I mean, they had many examples, but no systematic classification. And finally, the classification was given by Christian Baer. And again, very interestingly, by doing a geometric construction. And the geometric construction of Christian Baer is the following one. So assume you have a space on which there is a Killing spinor. Then the trick is to construct a cone on this space. So this is M. So I'm constructing a cone on M, which is the product of R plus with my M. And of course, I'm putting a metric which is dr squared plus r squared g. So of course, I'm started from my mg, which is the basis of my cone, if you want. And now the trick, which is wonderful, is that imagine on M you have a Killing spinor. Then there is a natural way by which you construct a psi bar, which is a Killing spinor on, which is a spinor field on Cm. And the fact that psi is Killing spinor implies automatically that psi bar is actually parallel, which means that the equation, which was this equation here, becomes the equation that the derivative for the extended extended covariant derivative on the cone is actually 0. So this is the equation you get. And of course, as soon as you have a parallel object, you know that the allonomy group reduces, and therefore you can do the full discussion. This is the end. So my concluding remark are the following one. The whole point was to highlight several instances in which the theory of general relativity either triggered the study of new objects in mathematics, and of course that was the case of the generalized metrics, or the case of bundle geometry, that was the case of Killing spinors, or changed the point of view of mathematicians. So of course, after the introduction of the Ricci curvature by Ricci, people got the feeling that it was not a good idea, didn't bring anything. But actually, of course, it's a very critical element because it's the basic constituent of the Einstein equation. Or suggested new approaches like the Ricci flow, or even led to missed opportunities. So I think, as I mentioned, really the most extraordinary things which happen in this connection between the general relativity and mathematics has been the study of the solutions of the Einstein equation. And as I mentioned in my introduction, initial work by Demetrios Christodoulou and Kleinerman, which was such a long paper that finally it was not published as a paper but as a book, 600 pages. I was one of the referees. It took me a year, but interesting exercise. But after that, there have been many other papers, still many difficult ones. For example, one which tells you that you must develop a singularity in the space-time with a given initial data, which is joint work between Christodoulou and Kleinerman. If you put together, it's more than 1,200 pages. So, because you need the book by Christodoulou on waves, and you need the paper, which is a 400 pages paper. So that's a substantial piece of work. Anyway, thank you very much.
Thank you very much. Any questions, comments, from the background, please?
My name is Nunes Lectures, and I conduct an experimental research work here in U.Porto for my PhD, which I measured the weight decrease of elementary particles as they rotate on a brass gyroscope. And this experimental research work that is now in mature phase shows that the principle is not found in nature. And the result is supported by the topological theory published in Russia. And I am now in the phase to do a prototype and show the professor that it works. So, according to my framework, which is non-relativistic, the Michelson model experiment was not conducted in that century. Because some critics in the last century to this experiment, they said that if two effects of light travel in the Michelson model experiment cancel each other, the final result is not null. It's null. So there was another setup of making
only one microphone in the room, and this is a too
Did you,
extensive question.
I sent you an email about with these results. Did you receive my email? Have you learned about these results?
No, I'm not.
Okay, so I have sent you an email, so if you have something like that, you can send me an email.
Thank you very much for this very beautiful lecture. I would like to actually, there are many things I think mathematicians could help physicists. I work on general relativity for many years, and there are so many things that a mathematician could help us. Well, you wrote what I believe is the twister equation, right? So.
No.
Some people call that twister equation.
No, twister equation is something else.
Okay, so that's precisely the type of things that we would be enlightened about. So if you solve for psi bar,
yeah.
What can you say about the physical solutions of the Einstein equation? So that's a mathematical equation.
Mm-hmm.
Why we are interested in the configurations of the metric for, let's say, a given energy momentum tensor. So that's one question.
Yeah, well, let me say maybe a few more words on this. One thing which has been noticed by the physicists immediately when they considered the killing spinors was the fact that, as I said, it's an overdetermined system. So in order for this to exist, you need the metric to be Einstein. So it should satisfy the equation. Ricci is a multiple of the metric. But then that was not enough, because there are many other constraints. And in particular, there are constraints on the shape of the Weil tensor, which has to be very degenerate in some way, and so on and so forth. So the way which has been really useful has been, because you have a parallel object, then you can look at the list of possible holonomy groups. And then from this list of holonomy groups, you can really have a pretty full description of the spaces. And of course, then you have to identify among these groups which ones can be the cone, because the metric I wrote is not just any metric. The metric is a very specific structure. In particular, it has a one-dimensional transformation group, which are the homocities by construction, because you build them as a cone. So now you have to look back among the ones with special holonomy, at the ones which have homocities, and then you can come up with a pretty complete description. So among the beautiful examples, which actually were identified by physicists the first time, was the so-called squash 7 sphere, which is a very interesting metric on the 7 sphere. So you have to think of S7. So I told you in supergravity a number of objects in 7 dimensions are interesting. Well, for mathematician, S7 is a very interesting object because it lies in the square of the quaternions, and therefore this is a round sphere in the sphere of quaternions. And of course, if you look at, there is a natural action of the unit quaternions, which are of course like S3 on S7, and if you look at the quotient, it's an S4. And why do we call it this, the squash 7 sphere? Of course, if you look at the very round sphere, it naturally, there's a very beautiful example of a Riemannian submersion of this ordinary metric on the sphere, on the ordinary metric on S4, and with S3 as really ordinary fiber. But actually, if you uniformly, you remember I introduced my factor phi when I was talking about Kaluza-Klein. If you use as a factor not the factor 1, but if you use a uniform factor which is not 1 for a very specific choice of the factor, you get a new metric, let me call it G prime, on S7, which is the squash 7 sphere, which is still a Riemannian submersion over this, but which has the property that its Ricci tensor, Rg prime, is again a multiple of G prime, and with the existence of a killing spinor. And this was really discussed by a physicist extensively, because, I mean, of course, you have to, the exact value of the radius of the way you squeeze all the S3s in this vibration, of course, is a really beautiful construction. Actually, you can think of it even as sitting in H2, and you look at, when you are in H2, well, you can look at how the, I have to, well, I'm sorry, well, maybe I skip it, to be a bit too technical too. You can think of it as a distance sphere in a projective space of a higher dimension. And therefore you can really compute everything completely explicitly, but actually this was done by physicists first, because they were very interested in the context of supergravity with this very specific squash 7 sphere.
My wife and like to hear your reaction. To my mind, the most beautiful example of mathematics in the last topic you mentioned, supergravity, was the demonstration that the energy is positive in general relativity. Probably you are aware of this result by Yao and by Witten, but I think it's such a beautiful example of using just mathematics and showing a very relevant physics problem. So,
sure. That's
okay.
No, indeed, I just gave a sample. I mean, you can make another lecture with a totally different sample. No problem. No problem. I can even do that. I mean.
Some more questions, please.
So you mentioned Hermann Weyl introducing gauge theory, and also how Kaluza and Klein anticipated bundle theory. But to what extent could they have anticipated non-abelian gauge theory? Was this, I mean, certainly Hermann Weyl knew everything about the groups, huh? So was this another missed opportunity somehow?
Yeah, you're quite correct. Actually, as you know, I mean, the Kaluza-Klein theory, initially, the parameter was just a real parameter. It was just a line. And there, to look at this as a bundle doesn't really useful, because there is a line, the line is contractible, and therefore there is no topology in this. Of course, as soon as you introduce S1, then the bundle may be non-trivial, and then you have something more interesting happening. But this happened only with Klein somewhat later. So I've not spotted, maybe you can spot that Hermann Weyl reacted to Kaluza-Klein saying, oh my goodness, we can do more. But I don't think so. I mean, the really non-abelian gauge theory occurred with the Young and Mills much later. And again, it was the idea of doing a classical theory whose quantum deformation will be the first stage of a full quantum theory. Nobody knew how to do a quantum theory of strong interaction, so they started to study something which would be some kind of classical analog. That's what they did.
It was a missed opportunity because Young and Weyl coincided at the institute in Princeton.
That's correct. So I don't know that. I mean, maybe we should ask Yang about that. While it's not possible anymore, so it's true. No, you're completely correct. Completely correct.
Yes, you mentioned the Ricci flow was in connections with mathematics of relativity, and maybe I missed the point, but Ricci flow is a gradient flow first order in time, while Einstein equations are second order in time coming from operational principle. What is really the
No. Well, the connection is the fact that you want to describe the Einstein equation in 4 dimensions, okay? And instead of using the field, which is this metric, indefinite metric in 4 dimensions, you decompose this metric in 4 dimensions into 3 objects. So forget about the so-called lapse function. So you forget about the function, you replace it by the description of a curve of metrics on the 3-dimensional hypersurface, and the curve of bilinear form, which is the second fundamental form of this hypersurface. Okay, so it means that solving the Einstein equation, and I wrote a translation into this new language that is replacing G by the curve GT and the curve KT. Forget about phi t for the moment. Then you replace the full 4-dimensional Einstein equation by the evolution equation and the constraint equation. Okay, but this. If you look at the equation, if you write it in a certain way, the evolution equation tells you that the second derivative of the metric is more or less governed by Ricci, by minus Ricci. That's the equation you get, plus some junk, which is not junk because the junk has to be there. If the junk is not there, it's not, the geometry doesn't fit. But anyway, it's not what counts for you in terms of PDE, okay? So this is the initial motivation for some people. It was for Thierry Aubin to look at deforming a metric in the direction of its Ricci curvature. Because it was, in a sense, spontaneously, if you've done the translation I've done, the variation of the metric was governed by the Ricci curvature. But the one which is given by the Einstein equation, it's not the first derivative, which is Ricci, it's the second derivative. So, of course, if you find the second derivative too difficult, you go to the first derivative. Of course, you change completely the PDE nature of the problem. You go from something hyperbolic to something which becomes parabolic. And anyway, but this was the motivation. So that's why he started to deform metrics in the direction of the Ricci curvature.
It was a pure mathematical
Yeah, appropriation of this, the fact that there was this linkage between the two. Is that clear? Or?
More questions? Okay, so if not, Rob, please.
It's just a comment because you mentioned that physicists were not interested in a Lagrangian who gave no equations of motion.
Yeah.
And the fact is that in condensed matter, which is by field, those are popping up all over the place.
Okay.
Terms in the Lagrangian.
Fantastic. So we need you. We need you. We need you.
The topological invariants are physical quantities of great significance from the experimental point of view. So maybe we should have paid attention before.
No, you're completely correct. But it's interesting to read the comment by Langsource by saying, well, this Lagrangian, I don't discuss it. And nobody noticed it until some years later. So thank you.